In this video I'm going to look again for a second example at converting from denary base 10 to floating point, normalized floating point. So I'm going to start off with a little bit of a more tricky example this time. I'm going to try and create minus 4.25, which is obviously in denary. And I'm going to try and convert that to normalized floating point representation. So first stage, so I'm going to try and put this into fixed point notation. It's a nice easy starting point. So fixed point, it's got 5, it's got a binary place, and it's got 3 on the right and 5 on the left. So the first of the binary positions to the left of that is a 1, then a 2, then a 4, then an 8, and then because we are using 2's complement, we have a minus 16. The 3 binary places to the right are a half, a quarter, and an eighth. So if I want to create minus 4.25 in fixed point notation, I know it's minus. I know this leftmost value is minus, so I'm going to choose 1 minus 16s. So from there, I need to work forward to get to minus 4.25. To do that, I will add 8 initially, which will bring me up to minus 8. So I'm working at minus 8 level now. I'm going to look at 4. If I add 4 to that, then I've gone too far, because I will not be able to get back the other direction in the 4.25. So I'm not going to have a 4, but I will have a 2. So minus 8 plus 2 is minus 6. I'm going to add a 1. Minus 6 plus 1 is minus 5. I'm getting close. I want to create minus 4.25. Well, minus 5 plus a half will bring me to minus 4.5. So I'm getting closer. So I'll have a half, please. That'll bring me to minus 4.5. Now I want to close that final bit of a gap. So I want to have a quarter there as well, which will bring me to minus 4.25. Yes, that's correct, because that's a half and it's a quarter. That's 3 quarters together, 0.75. I started off with 5. A quarter positive, 3 quarters positive will bring me to 4.25. I don't need any of those. So in fixed point, this is fixed point binary. The representation of 4.25 is that fixed point binary number along there. I'm going to move to normalized floating point next. So I'm going to go to normalized floating point. Now, a normalized number that is negative must start with 1, 0. So if it's negative, it has to start with 1, 0. A positive normalized number would start with 0, 1. So in this case, we are dealing with a negative number, so it must start with 1, 0. So that means that I need to move this binary place along. I will need to move this binary place along once, twice, 3 times, 4 times in order to create a, oh, that's not correct. It's a 1, 0. Let's try that again. I'll move this binary place along once, twice, 3 times. And I will have a 1, 0. Because it's a binary, a negative number, it doesn't matter that the ones on the left will be 1s. That's okay. So I can just sandwich it on here, and that'll be a 1 move, a 2 move, a 3 move along. So the normalized version of this fixed point binary number then becomes 1.0 1, 1, 1, 1. In fact, I can stop there. So it becomes 1.0. So I'll have the position here, 1.0, 1, 1, 1, 1. Excellent. So this then is my mantissa. It contains my actual numerical value itself. I can say that I have got a 1, 2, 3, 4, 5, 6.6 bit mantissa. 6-bit mantissa. Now, in order to get back to the original number, I also will need to have an exponent. So I can return the binary point to recreate the original number again. I move my binary point once to the left, twice to the left, 3 times to the left to create this number. That means to recreate the original number, I will need to move the binary places 3 to the right. So I will have a positive exponent value because it's 3 to the right, that's plus 3. I'm going to go with a 4-bit exponent. Now, the positions of the binary values is pretty straightforward for a 4-bit exponent. I'm just going to do a 1, a 2, a 4, and I'm going to stick to my 2's complement and have that as a negative 8. Not that it matters terribly in this example. So I want to recreate a plus 3 on my exponent. I can do that with a 2 and a 1. And those will be absent of 1s. So this then becomes minus 4.25 represented in normalized floating point binary. It's important to note that the binary place is always between the most significant bit and the adjacent one within the mantissa itself.